My name is Maria de Pau with ZID 5464010, and I'm going to go over the experiment of understanding the solar system using the gravity and orbit set simulation. Before that, defining the three Kepler's laws. The first law is the law of ellipses. Every planet moves along an elliptical orbit with the sun at one of the two foci. That means that no planetary orbit is perfectly circular, but rather an ellipse. Excuse me. Kepler's second law, the law of equal areas, states that a line segment joining a planet and the sun sweeps out equal areas during equal intervals of time. This law implies that a planet moves faster when it is closer to the sun and slower when it is further away from the star. And finally, Kepler's third law, the law of harmonies, states that the square of the orbital period of a planet is directly proportional to the cube of the seven major axes of its orbit. Moving on to the simulation, question two, going into the planet and moon scenario and assuming Earth and the moon for both objects. Does the planet move as the moon orbits? It does, and we can see how Earth moves, and this is because both celestial objects orbit the center of mass of the orbit, so it's not just the moon orbiting around Earth. It's the moon orbiting around the center of mass of the orbit, and so does Earth. In questions 1, 4, and 7, for the planet and the star system, Earth and the sun, um, this was different because we were dealing with the sun, which is an object of much greater mass than Earth, and thereby the center of mass in the orbits was super close to the sun, and thereby we couldn't even appreciate motion from the sun. This is what happened in both in questions 1, 4, and 7. Even when the mass of Earth was increased by a factor of 2, or the mass of the sun was increased by a factor of 1.5, the center of mass of the orbit was still too close to the sun. So the planet-moon center of mass is different from the sun planet center of mass because the difference in the order of magnitude between the masses of Earth and the moon isn't as large as the difference in the order of magnitudes between the mass of Earth and the sun. And now taking the star and planet in the standard configuration to be the sun and Earth, when the grid lines are turned on in the simulation, we can see the distance between each margin in astronomical units is 0.5 AU. This is because the distance between Earth and the sun is 1 astronomical unit, and there's 2 grid lines between Earth and the sun in the simulation. Um, by moving planets closer or further away from the sun and altering the velocity vector, so making the orbital velocity faster or slower to get completely circular orbits, we find a table relating planet distance and orbital period. When the planet was located at 0.5 astronomical units, the orbital period was found to be 123. For 0.75, 1.5 astronomical units, the same was done as well as for 2 astronomical unit difference. And those were the orbital periods observed. In order to understand that these results followed Kepler's third law, we had to graph Kepler's third law. So basically square the orbital periods that we obtained, cube the planet, the orbital radius that we chose, so from 1.5 AU to 2 AU, and then graph those points, and by inserting a line of best fit, linear, we should see the direct correlation, which would indicate that the results follow Kepler's third law, and they do. Um, Finally, understanding what planet has the fastest and what planet has the slowest orbital velocity. To do this, we would have to figure out a formula for orbital velocity, and we can get this by deriving the formulas for centripetal force and the formulas for Newton's universal law of gravitation. If we equal both of those formulas, will arrive at v is equal to the square root of gm over r as the formula for orbital velocity. And we can see that the only variable that changes from planet to planet is the radius, the orbital radius. Thereby, we would expect Mercury to have the fastest orbital velocity since it's the one that's closest to the sun. And the planet that we would expect to have the slowest orbital velocity would thereby be Neptune, being further away. The reason for this is that, as previously stated, orbital radius is the only one of the parameters that changes from planet to planet. G, the gravitation constant, is the same, and M, the mass of the sun, is the same for all planets in the solar system. Thereby, the radius, the distance between both objects, is the only thing that changes. And what I learned during this experiment was the dynamics of the solar system and how much of the distances between planets and the sun, or the planets and the moon, affect the eccentricity of orbits as well as the orbital periods.